Welcome to Embedded. I'm Alicia White. My co-host is Christopher White. Apparently, some of you like knowing about the inside of the compiler. So we've invited Pierre-Marie de Rodat to talk about the inside of a software debugger and get even further.
Hi, Pierre-Marie. Welcome to the show.
Hello. Thank you for having me here.
Could you tell us about yourself as though you were on a panel at a conference?
Okay. So I'm Pierre-Marie de Rodat. I'm a software engineer at a company called AdaCore. So on a technical standpoint, I'm a free and libre open source software advocate. I like working on tooling in general, and especially software development tooling, compilers, and static and dynamic analysis tools such as debuggers, code coverage, and that kind of tools. And that's pretty much it. What I love in software development. I had an engineering degree in a French school called EPITA, and I've been working at AdaCore for 4 years now. And I'm working there on topics that I love, that I described earlier. And I'm mainly a host, working on host tools in native configurations, but I also have to work sometimes on cross-tool chains, so I have some contact with embedded development.
Excellent. We're going to ask you about many of those things. But first, we want to ask you for short answers, and we will, of course, be asking short questions in order to get them.
That was backwards.
That was totally backwards. Maybe we should ask him to just give us answers, and then we'll generate questions.
Sure. I don't think that would work.
So, first question, command line or IDE?
In the ideal world, I would be working in IDEs, but it's hard to change, and I still work on command line.
Favorite language?
Nah, that's a tough one. Let's say Ada to be an advocate.
Technical tip everyone should know.
To be on topic, GDB has a Python, uses Python as a scripting language for extensions. It's really useful and powerful.
Yeah, we've been using that. It's cool.
Yeah.
Huh. Sounds like I should try it. Oh, it's your turn.
It's my turn. Favorite keyword?
The hard question. Let's say package.
Package. All right.
Import.
Yes.
Almond croissants, chocolate croissants, or plain croissants with jam?
I would say
if you say
chocolate.
Toast.
Yeah.
Oh, all right.
Yeah.
Favorite movie or book or other media that you encountered in the last year?
I think this will sound like a classic, but I just read the Foundation book from
Asimov.
Yeah, from Isaac Asimov, and that was a really good discovery for me.
Cool. All right, let's get into bigger questions. People who come to embedded systems from the Arduino world and people without a software background don't necessarily know what a debugger is. A compiler, okay, that translates source code into machine code. Or we don't have to talk about the linker. That's too deep. But what is a debugger, and why does it matter? Can't we just use printfs?
Yes.
There's so many little questions in there.
Okay. Well, first, I think it's a good introduction to debugging in general to acknowledge that, well, programs, once they are ready to run on your target, your computer, or whatnot, It's essentially a black box. I mean, it gets inputs. Sometimes it produces outputs, but you don't get to know really what's happening in there. And debuggers, well, I think there are tools that turn these black boxes into some kind of glass. You can see the execution happening. And so when things go wrong, like when you have a bug, well, you can actually look at the inside of your program and found where this is going wrong and where is your bug.
It's kind of magical. You go from trying to figure out what's wrong based on what it's telling you to actually being able to see inside. So I like your black box example.
This is really how I feel, and I think people can relate when you have you have your program, it's yours, you've written it, and it's not working. And if you don't have a debugger and you've used one previously, for example, I don't know if you're working on a system that doesn't have a debugging probe, you feel powerless and you're like, oh, I have to recompile over and over again, flashing the LEDs to hope to understand what's going on. And with a debugger, it's magical.
So you mentioned earlier about cross-compiling, and you just mentioned a debugger probe. These are more embedded topics where in software, usually your debugger is running on the same system that you're running your code on. But in embedded software, often your computer compiled your code and your computer has the debugger, and you have to use JTAG or SWD in order to probe into the system. And I like that. And we're actually going to talk to some folks from Seger in a month or two. So we're going to talk about debug probes and how that path works later. I want to focus on the software debugging. And that leads me to the question of, well, how does it know about my program? Does it just interpret my executable? That doesn't seem right.
Yeah, indeed. Actually, I like to think that you can think of your debugging technology as a kind of pipeline. You have the front end, so it's. I'll take the example of GDB. So indeed, GDB is the software that runs on your computer, on your host computer, and you have some part of it. So if it's a native program, I don't know, Firefox, everything is in your computer. But if it's in your cross configuration, then you have a small piece of debugging technology that runs on the target and that communicates with the host program. That is your debugger. But I would say people could disagree, but the most complex and smart part of the debugging technology is happening on the host.
Okay, so let's talk about that. So it's a bit of a mystery, right, to some people how this works, because, I mean, one of the great things about debuggers is you don't have to run your program at full speed and then try to pick up the pieces afterwards. You can step line by line or instruction by instruction. You can leave it sitting there at a particular line and go have lunch, think about it, and come back. So how does that actually work? How is the debugger interacting with the executable in such a way that it's got kind of full control and the executable doesn't even know?
Yeah, this is this is the most fundamental part of debuggers. Talking about native programs, generally the operating system enables debugger to stop the execution of a program to inspect it. So this is, I would say, the first basic operation is to ask the program to be stopped, interrupted temporarily. The debugger can also ask with system calls to have the program to execute only one instruction. And the last piece is the debugger can modify the code of the running program to put instructions that will stop the execution of the program and get back to the debugger. So this is the famous breakpoints. I guess you're familiar with them.
Oh, yes.
And also, well, in embedded programs, sometimes you rather use your hardware. You have special registers. Well, they are generally called debug registers, and you can put the address of your code or of the place in the code that you want, where you want to stop. And the hardware, when it will try to execute this address, it will stop and call out for the debugger. So this is the third major step for debugger. And so this is how you can control the execution flow of the program from the debugger.
Okay.
Does that make sense?
Yes.
Okay.
But the way you're describing it, where there's the ability to stop and to start and to step through, and even the hardware or the debug registers that allow you to have an interrupt that causes the system to stop and have a breakpoint.
Mm-hmm.
Those all make sense, but how does the debugger itself know about the program? How does it know where main is? How does it know that my variable X is in a register or in memory? How does the debugger know anything about my program other than the ones and zeros that are in the executable?
Yeah, this is the really interesting part of the debugger, and the part I prefer personally as a as a debugger developer. So the debugger has two ways to get information. The first is to directly interact with the program, and generally it means being able to read and write registers and memory. So this is how the debugger can know about the state of the program, where the execution is happening at the specific moment. So to get the program counter, basically. And on the side, if you want the debugger to know about your program, to get back to the source level, you have also to provide debugging information to it. And this is where you generally, for example, for GDB, you pass just the ELF binary, and this is where the debugger will read the list, all the source information, which functions are available, which variables where, and so on. So using these two sources of information, the debugger will understand the state from the process and interpreting it in light of the debug information.
And so the ELF file, this isn't my dot out, is it? I mean, in Linux, it would be dot out. In Windows, .exe.
Yes.
Oh, it is that. Okay.
Yes. The program that you normally just execute. It's the file that contains the program. Well, actually, it depends on the toolchain. On Linux, generally, debug symbols, they are in the same file as your program, but they can be in another file. On Windows, for example, so you have your .exe, that is the program that you want to execute, but the debug information is in a file called .pdb.
And in Linux, one reason you would want it in a separate file is so that you could have production code that was harder to debug, and yet still the developer would want to be able to debug. So you'd release the, I don't even know what the word, undecorated?
Stripped.
The stripped version. You would release the stripped executable, but you'd still have the ability to debug using this separate file.
Yes, that's true. And yes, so making it harder for people that don't have the debug information to debug is one reason. And another reason is that debug information takes sometimes a lot of space. Sometimes it doubles the size of your executable. So you just want to distribute debug information only when needed.
And so for those of you keeping score in the embedded world, you can bet that the debug information does not live on your processor.
Pretty much ever.
Yeah.
Okay, but back to native compiling. So what is there a name for the debug information? Is there a word I should know or something? Is this where DWARF comes in?
Yes, exactly. Actually, there are... So debug information, it's like a principle. It's the compiler telling the debugger how to interpret the state of the program. And there are several formats that were created to encode this information. There is an old one called stabs that was used in GCC. It was a default in GCC quite a long time ago. And it's not very powerful. You can't describe complex things. On Windows, generally, what you use with the Visual Studio toolchain is code view, and DWARF is one of these formats. It's used mainly in the GCC and LLVM world. It's very expressive. You can think of it as almost as a language, and it's even Turing complete. So these are the main debug formats. So formats in which the compilers encode this debug information using this.
Okay, this is interesting because I've never really known about DWARF, except it's the thing that the debug stuff goes in. So that's embedded in the ELF file.
The executable or the separate debug file.
You said it was Turing complete. What does that mean? It's what can you... I'm used to things being symbols, like, okay, my variable X is at offset whatever, and that kind of thing. But it sounds like this has actual scripting built into it. What does that do? What can you do with that? Or what does the compiler do with that? This is fascinating. Sorry.
I agree.
If you enable optimizations in your compiler, your variables they are not going to disappear. But say if you have a loop variable like an index, the compiler doesn't have to create to put the value of this variable in a register or in memory. But so because it could be more efficient to directly add the offset to some address, for instance. So if I take an example, if you are iterating on an array, you have an index that you increment when the loop executes. So the compiler doesn't have to keep in memory the value of the variable, but it might be possible still to recover the value. And debug information, if the format is powerful enough, you can express there this different step of computation that enables the debugger to recover the value, even though its value is not present anywhere in the state of the program.
That sounds really useful. Why don't I have that?
Well, you probably do. Are there debuggers that are better at that than others? Because I've noticed with for example, IAR, if you have optimization turned all the way up, stepping through is like just pachinko. It's balls bouncing all over the place, and but GDB seems a little better at that. Are there debuggers that are better at that, or is it just my imagination?
To be fair, no. It's so the important word is that's possible in debug information, but really the debugging is compilers and debuggers working hand in hand. Sometimes the compilers will do optimizations, and then they won't, if they do optimization too hard, or if not enough effort has been put into debug information generation, Well, the compiler won't know how to compute the values of your variables anymore. And so this is where in GDB you will try to print a variable in optimized code, and it will say optimized out, and you won't be able to see the value of the variable. So DWARF enables to describe complex computations to recover the values, but the compiler has to provide it. It has to tell the debugger how to do it.
So it's definitely compiler dependent.
Exactly. And well, there are efforts put into this, having good debug information with high level of optimizations, but it's really hard.
Yes. So my compiler takes my .c file or .c++ or Ada or whatever compiling file source I have. And if I have debugging turned on so that it generates the DWARF information, but I also have optimizations turned on, in a perfect world, the compiler would be able to create code itself in this DWARF language that would describe how debugging should happen. And in an unideal world, the compiler doesn't generate anything useful, and my optimized code doesn't run the way I expect. Is that a good summary?
Exactly. Yeah, this is what happens. And even to take another example that people can relate to, the more optimization goes on, the more the compiler shakes the generated code. So some instructions to implement a statement will get out of the loop, or will move up or down. And in the debugger, you will see execution goes to line 10, and then 8, and then 11, and then goes back to line 8, and then 7. So the more the compiler transforms your program to be fast, the more it will be the execution will be different from what you intended previously.
And when we say the execution won't be what you intended, we mean as you step through line by line,
yes,
various instructions are going to bounce around. It's not that you wrote a program and it doesn't do what you want. It's that at the instruction level, when you're debugging, it might not do what you expect.
Exactly. Okay. And more precisely, actually, the compiler is allowed to do whatever it wants with instructions as long as it respects the semantics of your program. And this is where compiler people will tell, be careful with undefined behavior, because we as human, we think the program is going to do this because we say +1. But if actually we reach an undefined behavior, the compiler is allowed to do something completely different.
As long as it does what you told it to do, it can do whatever else it wants in its free time. And if it thinks you're stupid, which compilers often think I'm stupid, it will do what it thinks it needs to do in order to do what I told it, but it won't necessarily do it the way I told it.
Yes. Well, it's not because they are mean, but they will do this. They will do this if you break the law. Like if in C you let me remember what's an undefined behavior. I think if you have a signed integer and it's already equal to the maximum value allowed for this type, and you do +1 on it, I think this is undefined behavior. And if this happens, well, the compiler can do whatever it wants to. Well, execution is not defined anymore, so it could very well erase your hard drive or.
Well,
the compiler is going to do that, but this is.
I thought you said it wasn't mean.
Mean compilers.
Yeah, as long as you break the law, that if the C standards say no, you're not allowed to do that, and you do it anyway, anything can happen. This is a rule of thumb.
I was going to ask if you had a favorite debugger, but now it sounds like it's the compiler and how it generates this debug information that's important. So maybe I should ask, do you have a favorite compiler?
I work almost all the time with GCC. So I wouldn't be able to say that something else is my favorite compiler. But yeah, LLVM is a pretty good competitor, I would say. I don't know. I don't have practiced a lot with other compilers, so I wouldn't. I'm not able to tell more. But to complete what you said, it's paramount that compilers generate good debug information. But on the other hand, it's very important for the debugger, well, first of all, not to have bugged itself, and to provide interesting features around that.
What kind of interesting features?
Well, I told about the Python API. Well, this is a good example. You can have that even if the DWARF information is not complete, or I don't know. And if it has, well, good features, so a feature that every debugger on Earth, I guess, has is being able to print a stack trace. So the various stack frames that those are the chain of calls that led to the current state. Does it make sense?
Oh yeah, I'm very familiar with the stack trace and what happens when you trace the stack and it says that you are at 0, 0. Beep. So that is an excellent feature, and when it goes bad, it can go really bad. RTOSes make that, or all operating systems, I suspect, make stack traces a little more complicated because you have different threads.
Right, yes. And some are better than others at being able to switch between them. I won't mention the other compiler again.
I was going to say, Chris, do you have any opinions about a particular compiler?
Let's just say GDB is pretty good at switching between threads, and something else, basically, you're in the running thread and that's it. I guess I wanted to ask how that works, actually, because I know we wanted to stay native, but on target, how does multi-threaded debugging work? How do you tell the target does that require a special piece of the RTOS that speaks to GDB?
This isn't really a fair question for him.
No. I can try to answer that. I'll first start with something I approximately know, which is the in Ada you can have tasks are first-class citizens, so they are part of the language.
Okay.
And GDB knows about where to look at in memory to determine the list of threads. So the debugger has to indeed to have some knowledge about let's say the task table on the target. It has to.
Okay.
And I've heard, so this is from an engineering point of view, this is not terrible because that prevents somebody from creating a new RTOS and to make it work like this in a debugger. The person has to enhance the debugger first. This is not terrible. And I've heard that people in the GNU community have started to formalize some kind of, it would be like debugging information, but for the runtime, something that would say, okay, so you want to know the list of threads, go there, so that a debugger wouldn't have to know every RTOS and language out there to be able to display the threads.
Okay.
So is this an extension to the DWARF debugging information, or is this something else?
I don't remember. No, it's not really DWARF. I would say it's complementary information that isn't encoded in DWARF. but I wouldn't.
Because it's part of the operating system, right? So it's more of
not really about the program, but it's not clear whether it belongs really to the language or something else. So I wouldn't bet on it. Okay. But anyway, it's more into debug information.
Is there debug information? Is there information intended for the debugger that I can read? I'm thinking about map files and list files, and I know those are compiler dependent how they come out, but most compilers seem to have something like that. Are these DWARF features, or are these debugger features? Does the debugger use them at all, or is this just output for the human eyes?
I'll talk about DWARF because, of course, this is what I know the most. DWARF is a binary format, so you won't be able to open it in your text file, but it has, you can use, I don't know if you know the objdump program. Yeah, well, it is able to output to decode the binary information and to present you in a text fashion. And actually, this is what I, as a compiler and debugger developer, use to check that the DWARF is okay, and that whether it's the compiler or the debugger that is wrong when things are not working properly. So, well, you can use this dumping tool if you're curious, but really, it's if you consider yourself as only a software developer that wants to make programs and not tool chains, it's not that useful. Well, I say that, but now if you know it and you as a user see that things go wrong, it could be useful to have a look and say, yes, I see this. So this is this variable that is not described properly, and to report the bug to the project that is responsible for that.
That brings up a question Chris noted down. How do you debug a debugger? That seems, it seems a little recursive, but what tools do you have? Do you have,
do you just run GDB on GDB?
Exactly.
Oh my God.
This is exactly what, so I guess if you have, if your debugger is in an IDE, so you have Windows, it's easier because, well, you have one window that you know. Let's say you put it on one screen, it's the debugger that you want to debug, and on another screen you can put the window that is the debugger of the debugger. But actually, well, I already had to do that. I had some bug in GDB, and so I ran GDB and GDB, and not to keep things sane. I put the prompt of the GDB that was debugged in red, and the prompt of the GDB that was debugging in another color, so I could know where I was standing. Yes. But it's possible to do this in only one console.
It would be a little confusing, but okay. So what program was the GDB that you were debugging when you were debugging the GDB? Sorry. I figured I could go on like that for like another half an hour.
Yeah, it's Inception.
Yes.
Debuggerception. It was a Jumi program that was just trying to reproduce a bug. In this case, it was an ADA program, probably with some complex type that GDB could not grasp yet.
All right, that makes sense. How many GDB bugs have you found? But that's sort of not the right question.
How many have you written?
Having a debugger that is solid is really important because I have to trust it. But it is a piece of software, so there are going to be bugs.
Oh, yes.
How do I figure out when the bug is me versus it? I mean, this is always a problem. I hear about people with compiler bugs they've found, and sometimes it's true, but it isn't as true as often as I hear about it. What kind of things would I need to do to start getting into GDB bugs? I mean, this seems like they should all be corner cases now.
Yes, actually, the bugs I see generally are not, well, we are talking here is a very specific kind of debugger bug. It's like you print a variable and GDB is displaying some value, but really it shouldn't be that value. Like GDB has been wrong decoding the states. This kind of bug, well, this happens not, it's very rare. And generally, a debugger bug will look like, oh, GDB has crashed. Okay, this is not the program that is buggy, it's the debugger, clearly. Or it will be like you print a variable and GDB will say, what variable? No, this is nothing. There is nothing called like that. So, well, as a programmer, you're like, oh no, I have two problems to fix. But you know it's not your program that is at fault, it's GDB. Otherwise, indeed, this can be a problem. But generally, well, if you manage to get that, you can always. So if you print your variable, it says 1, whereas it should say 0. Well, you can recompile your program with a printf that will display the variable, and you'll know which one is right.
Given that the DWARF debug information is compiler generated, how often do you have to figure out if the bug is in GCC or the compiler, in GDB, in the debugger, or in the compiler, in the compiler's debug output information?
Well, fortunately, it's also very rare. Generally, the kind of bugs I fix is something. It's not that I have a wrong result. It's that I have no result at all. So it's the example of, okay, I'm trying to print a variable and the variable does not exist, but I know it's there. So this is obviously a compiler or a debugger bug. So this is very, very, very rare. And when that happens, well, that's the kind of bug that requires you to be more focused than usually. You have to. This is where you have to take a lens and inspect closely what the compiler and the debugger do, and you get a bunch of dump files to see the various steps of compilation and debugging, and to identify on a simple example where things are getting wrong. Well, this is like an exploration. You have to see it like this. Yeah.
Yes. Most debugging is to some extent.
Yes.
So before we leave the topic of debuggers, I did want to ask about something you mentioned at the top of the show, Python scripting with GDB, which you mentioned is quite powerful, and I know people I'm working with do some of, but what sorts of things can you do with that, and why would I care?
The first thing that comes to my mind is something very useful, at least to native programmers, that is called pretty printers. So imagine you are working with a C++ program that uses vectors from the STL. In a debugger, if you will try to print this variable, you won't see the content of the vector from a logical point of view, like, okay, this is a vector of integers, it contains 10, 1, 7. No, what you will see is a record with all the gory details of the implementation of the vector. So you will see what the developer of the STL will see. Does it make sense so far?
Yes, so far.
So as a user of this vector library, you don't want to see that. And so one feature of GDB is the ability to provide special Python scripts that will be called whenever a vector will be printed, and which will be able to say, okay, this is a vector, the data is there, and there, and prints only the useful information in this stack of records, structures, and pointers, and arrays, and so on. So as a user, you will print the vector and see the list of integers between brackets, and you will be very happy.
Gosh, I've been doing a little bit with OpenCV and trying to figure out what I want to do when I move it from Python to C++. And it sounds like if I want to be able to look at intermediate images, I could use Python to be able to read my buffers and then put them and actually display intermediates. That's a little bit beyond the vectors you're talking about. This is showing images, but that's easy in Python. Would that work?
Yes, I guess so. Then maybe another option in this case maybe would be to call some debug function that is present in your program that, I don't know, would take a buffer in parameter and will dump it as a PNG image on the disk. That would be another option, but yeah.
Okay.
An option would be to write some Python code that will get the data inside the buffer and then use some magic Python library to output an image, even to open your file to your image viewer to display the file in one single command. You can do that.
All right. I just wanted to make sure that I understood how this was going to be useful to me. But I do want to change topics a bit because you also work on code coverage and you work for AdaCore, which of course, Ada is their language. I mean, not theirs. Ada is their preferred language. I don't know how to say that, but what do you do there?
Okay, so this is the first program I worked on when I entered in AdaCore. So yes, I'm working on a program called GNATcoverage. That is that is a code coverage tool, and I'm working on various aspects on this program. It's a program that strangely is not unlike a debugger in that it works hand in hand in the compiler, because it has to know about the program, the source level program, to produce a meaningful report, coverage report.
Okay, what is a coverage report?
Yes. Well, code coverage is it's a tool that is essentially useful to spot untested on unused code. So, for instance, if you create a function that has an if-else condition in it, and you write on the side a test for it, if the only use case you're testing is that the if condition is true, well, you have some part of the function that is not tested. And a code coverage report will tell you that. It will tell you, oh, these statements, they are never executed. You're not testing them, or maybe they are even useless. You could remove them. Maybe it's a feature that it's implementing something that you didn't want to implement on the first hand. So this is what code coverage is about.
All right. I do like unit tests, so that makes sense. Is this only for Ada, or is it language specific?
Well, code coverage is a concept that applies to potentially all languages. And GNATcoverage is the tool from AdaCore. It works on Ada and C. And it has some specificity that because it works really hand in hand with the compiler, we had to modify the compiler to make it work well. And so it's unfortunately for now, but we are working on some other alternative. It requires to have a specially modified compiler.
That's a little unfortunate.
Yes.
But not uncommon. I mean, you have a tool that is well integrated into a tool chain. So yeah, I can see how that happens.
At the risk of reopening the GDB kind of question again, how do you...
No problem.
How do you verify that your code coverage report is accurate?
Well, there is no formal proof. Like, I have proved that in all situations the report is correct. Well, what we do is, like most projects, we have a test suite that we try to make as exhaustive as possible. That checks that curve coverage, the code coverage computations work as expected.
Okay. So you start with something that you know executes a certain way.
Yes,
either
exactly.
on paper or from some other tool, and then you verify that you get the expected result from your new code.
Yes.
Okay.
I was sort of hoping that he had some code coverage generator coverage tool debugger that inceptioned back to...
No, I wasn't expecting that.
Well, you're almost right, because at some point we to make sure the tool was let's say powerful enough, we computed the code coverage report on GNATcoverage itself. So you were not that far from the truth. Well, this is what's funny when you are developing software development tools, is that you can use them on your own tools.
How did it do the first time? I mean, how was the report, the coverage report, initially?
Well, for code coverage reports, it's kind of easy because you don't have to have a working code coverage tool to start writing a code coverage tool. So it works with the most basic programs. Now the hard part is how do you write a compiler in a language that has no compiler yet.
Yes.
But for code coverage tool, fortunately, we're safe.
When we had Fabien Choteau on the show last year, AdaCore was having a competition, Make with Ada. Is that happening again?
Yes. Make with Ada, the second edition, is currently running. So it's still a contest for Ada programmers on embedded targets. And unlike last year, where it was, I think, only focused on ARM targets, this year it's allowed for any target. So it could be AVR, PowerPC, Spark, Leon, or whatever. It started mid-May, and it will end on the 15th of September. So it's kind of late, but not too late if people want to subscribe. And it's a good thing to keep in mind that we the jury, what's important is quality over quantity. So there is 1 month and a half left before the end of the contest, but you can still do something that can be appreciated by the jury.
And what contests entries last year were your favorite? That may be imprudent. Which ones won?
No, I can. I think I haven't had personally a look at all the entries last year, but there is one of them that I keep in mind is Stefan Carrez. He wrote an Ethernet driver for a chip on an STM32 board, and so he wrote the full stack, like the Ethernet layer, the IP layer, and the TCP layer. It was really a nice piece of work, and
everyone should have to do that once.
In Ada.
Yes, in Ada, and he put a lot of efforts into documenting documenting his design decisions. That was instructive.
That sounds pretty amazing, actually. All right, any advice for people who are thinking about entering this year other than quality over quantity, and you don't have a whole lot of time, but you have enough time if you get started soon?
Well, it's pretty much it. If you focus on good development practices, like good documentation, have a good test suite, and compute code coverage, or use formal methods, it's really a good point. And well, that's pretty much it.
All right.
Yeah.
Seems like a good place to wind up the show.
Okay.
Pierre-Marie, do you have any thoughts you'd like to leave us with?
I would say the devil is in the details, and this is probably where your bugs are. So don't hesitate to dive into how your programs work to understand and to find the bug.
I like that. Thank you.
And this is a pretty fun way to program, I think.
Yes. Our guest has been Pierre-Marie de Rodat, software engineer at AdaCore. Thank you so much for being with us.
Thank you too. It was a great pleasure to have this talk.
And thank you to Christopher for producing and co-hosting. And of course, thank you for listening. I have a quote to leave you with this week, and of course it's from Ada Lovelace. As soon as I have got flying to perfection, I have got a scheme about a steam engine. Embedded is an independently produced radio show that focuses on the many aspects of engineering. It is a production of Logical Elegance, an embedded software consulting company in California. If there are advertisements in the show, we did not put them there and do not receive money from them. At this time, our sponsors are Logical Elegance and listeners like you.